Given, a string number of digits 0 to 9 and an integer target. Rule, insert binary operators plus, dash, or asterisk between digits. Group consecutive digits into multi-digit operands. Operands cannot have leading zeros, except the single-digit 0. Output, all expressions that evaluate to target. Example 1, number 123, target 6. 1 plus 2 plus 3 equals 6, and 1 times 2 times 3 also equals 6. Both expressions belong in the answer list. Example 2, number 232, target 8. 2 times 3 plus 2 is 8 because multiplication binds first. 2 plus 3 times 2 is also 8 for the same reason. Again we report both strings. When you're forced to discover every possible operator combination that hits a target, you are dealing with a classic combinatorial exploration. We must use backtracking to step through the string, splitting our timeline at every single junction. At each gap, we test 4 distinct realities, inserting a plus, a minus, a multiplication sign, or choosing to insert nothing at all, fusing the digits into a multi-digit number. We build a recursive multiverse to check every path. But as we branch, we run headfirst into the iron rules of operator precedence. Imagine our recursive path has built the expression 1 plus 2, holding a running total of 3. If the next choice is to multiply by 3, a naive algorithm simply multiplies the total, giving us 9. But standard math dictates multiplication happens first. 1 plus 2 times 3 must equal 7. Our running history is trapped by its own past decisions. To solve this without reparsing the entire string from scratch, we equip our recursive engine with a mathematical time machine. Alongside our running total, we track last value, the trailing term multiplication would bind to. When the last operator was plus or minus, last value is that operand with its sign, like positive 2 after 1 plus 2. This tiny piece of metadata gives us the ultimate defense against future multiplication disruptions. Last value depends on which operator we just used. After plus, last value is the signed operand, plus 2. After minus, last value is the negative token, minus 2. After multiply, last value is the product built so far, plus 2 after 1 times 2. These 3 mappings define how the ledger tracks history. Now watch how our time machine beautifully unifies all multiplication scenarios using a single math invariant. Whether multiplication follows addition, subtraction, or an existing multiplication chain, the rule never changes. We subtract our logged history token from our running total to wind the clock back to its baseline, multiply that isolated history token by our incoming value, and add the new product back. By tracking implicitly signed historical metadata, consecutive blocks and negative chains naturally collapse into their perfect PEMDAS order in constant time. Let's observe the final branching choice, fusing digits. When we place no operator between digits, we build a multi-digit block. Those digits stay glued together as one operand, our single one becomes 12. Both the running total and last value update to that whole number, so the search can treat the block as a single atomic unit. But generating expressions requires one more strict constraint: we must prevent invalid digit combinations. If our backtracking cursor lands on a standalone 0, it can safely attach a trailing operator to it. However, it is strictly forbidden from joining subsequent digits to it to form numbers like 05. The moment a digit block begins with a leading 0, our engine actively sabotages that branch, cutting it off instantly to keep our expression list pristine. With our time machine handling precedence and our zero sanitizer guarding the boundaries, our backtracking loop safely completes its global sweep. The moment a branch consumes the final digit of our string, it compares its final running total against our target. If it matches, the fully assembled expression string is harvested into our results array. We have successfully broken down a brutal combinatorial puzzle into a clean, deterministic victory. We boot up our backtracking framework. We begin with our input criteria and our starting root node. This node represents the base of an execution tree, holding our current index, our string path, our running total, and our history ledger. We spawn this initial node at index 0, setting our mathematical baselines cleanly to 0. Every branch must have an explicit terminal point. The moment our tracking index steps across the final character boundary of the digit string, we have reached a leaf node. The system runs an instant equality check against our target. If the leaf's running total matches perfectly, we record the expression string in our results list. To evaluate both single digits and multi-digit blocks, we fan out one branch per substring starting at the current index. As the loop steps forward, we extend the slice one character at a time and read each part_str. Each distinct slice gets its own operand value, parsed as an integer so our arithmetic stays safe from overflow. We embed a strict value sanitizer inside our branching logic to prune formatting anomalies. A standalone 0 is a perfectly legal operand, but it cannot be joined to trailing digits to form multi-digit numbers like 05. When the loop would extend past a leading 0, we execute a hard break and discard that branch. Now, our execution pathways diverge. The first number at the absolute beginning of our expression has no history behind it, so it cannot legally support a preceding operator. Our engine detects this root condition and seeds both our running total and our history container with that baseline value, skipping operator evaluation entirely. For all numbers beyond our initial anchor, the tree splits into 3 operator branches. Addition and subtraction append their symbols and update our total normally, adjusting the history ledger's sign implicitly. Multiplication applies our precedence rule, unwind the running total by last_value, multiply that term by the new operand, and fold the product back into the total. N is the length of number, capped at 10. Time is order 4 to the n in the worst case. Each gap chooses whether to merge digits or insert plus, minus, or multiply, so the search enumerates expression shapes exponentially, but the small limit keeps it tractable. Space is order n for the recursion stack and the path string, plus storage for the answer list. Here is the full pseudocode. Add operators starts backtracking from index 0 with an empty path and 0 totals. Backtrack tries every valid substring from the current index, breaks on leading zeros, anchors the first operand without an operator, then branches on plus, minus, and multiply. Multiplication uses running total minus last value plus last value times current value.